right. Good morning, good afternoon, good evening, everybody, depending on where you are. Welcome to the OPAL-RT learning journey. First, let me introduce myself. My name is Etienne Leduc. I'm offering manager for the energy market at OPAL-RT. I'll be responsible for hosting this presentation today. And I'm glad to welcome also Mehrdad Kazem Tabrizi, a smart grid simulation specialist at OPAL-RT Technology. So he did the biggest work to prepare the capability demonstration that we have for you today. Hello. At the end of the webinar, we'll have a question and answer period from the audience. So please feel free to start sending your questions at any time through the Q&A pop-up menu that you have at the bottom of your screen. So just a bit of background before we dive into the demonstration. So HyperSim on Demand is really an evolved concept from OPAL-RT. We've been presenting this HyperSim on Demand since a couple of years now, and we keep working on our roadmap to bring new capabilities to the market. And this is a milestone that we're presenting to you today. To provide some more feedback, some more context to why we're working on this is really the mission of the company. So our mission at OPAL-RT is to help the customers reduce their costs and delays for complex mechanical and electrical system design, prototyping and testing by providing high-performance simulation systems that are open and easy to use, utilizing commercial technology optimized for parallel computing with the ultimate goal of making real-time simulation efficient, precise, and accessible to all. And furthermore, the vision that we have is that we were founded with the goal of democratizing real-time simulation. The vision is that real-time simulators will be on every engineer and researcher's desk, and imagination will be the only real limit to complex system design. Obviously, now with the cloud, there's a concept of having an engineer's desk that can also be on the cloud, but it really aligns with the vision of democratizing real-time simulation. And at the core of this capability, or at the core of every capabilities that we're working on at the moment, is really performance, which is a core value at OPAL-RT. It's really the focus of our dedication, our core business that enables all of these applications that our customers work on. So you all know about conventional HIL, SIL, PHIL, or RCP testing. Today, we will demonstrate capability of cloud-based HIL, SIL, RCP simulation, but that also works in parallel or benefits from the same work that we're doing on a connection simulation tool that we presented in other webinars, as well as the digital twin. They all share the performance at its core and some additional capabilities. So by working on this performance and on the cloud, we enable applications in all these fields. So to come back, I won't dive too much into the details of these other topics that we've covered in other webinars. I would invite you to look in OPAL-RT's Resource Center if you have more interest to know better about these different applications. But I just wanted to provide a bit of overview here of the different areas of application that we're working on with this cloud development. So there's one vision to help operations to respond to high DR integration with a high accuracy digital twin, where we would have a HyperSim digital twin, or it could also be RT Lab with ePhaserSim or Artemis, run on the cloud and be synchronized with the control center using data from the state estimator to initialize the simulation every 5 to 10 minutes and enable parallel testing and fast testing of EMT simulation or even RMS simulation in a fast manner so that we can optimize and maximize the number of tests that can be done to support the decision-making of the operations. Another area is the vision to help the planning more specifically. That relates, if some of you attended to the Australian Energy Market Operator webinar that they gave yesterday within the ESIG group. The goal is really to provide a connection simulator tool that will help OEM to perform interconnection and integration studies onto the grid and facilitate the planned connection process. And the goal here is to provide a really, really fast simulation that integrates OEM controls within with confidentiality of their IP. So really the challenge is to protect their IP, to have that behind a wall that allows manufacturer to connect their models, project managers to come and connect their models to this main grid and test all kinds of tests that they need to do to make sure that the plant will be properly integrated in the grid and facilitate then the connection process. And that can be done on, using an online web portal with the HyperSim EMT simulation service that's highly secure and confidential for all manufacturer IPs. And that also allows concurrent users launching several studies in parallel on several machines. So that's another area of application where HyperSim or RT Lab on demand could be used. It's the vision that we have to help planning. And today, the focus of our demonstration is really about the vision to help HIL, SIL, and RCP testing, also using either RT Lab or HyperSim, where distributed simulators can be used for either offline or real-time simulation, but really based on the cloud. So typically, the diagram that you would know is this one here. We'll have a host computer running HyperSim or RT Lab, and would then compile the code and load it on a real-time simulator, a hardware machine that we provide to interface with an external hardware device that would be under test. And the idea now is to replace, or not necessarily replace, but have a different capability than the real-time simulator here, and instead use cloud infrastructure to connect to different virtual simulators that could be any size, 4 cores, 16 cores, even more for larger models, and still being able to test hardware that you have in your lab using an Ethernet-based communication protocol. So for this demonstration we'll have today, there are a few core technologies that we used. So there's a centralized database to import the IEEE 118 bus model from PSSE to HyperSim. There's a high-performance Azure-based virtual machine running HyperSim on a Windows operating system. There's a low-latency, high-fidelity Ethernet communication, and you'll see we'll have absolutely no packet loss, so it really enables the HIL testing. And we have a cell-based wide area controller that's connected to this cloud-based HIL simulator. So without further ado, I will let Mehrdad say a few words before we start the demonstration.
Hello, everyone. Thank you, Etienne, for the presentation, and welcome everyone to the demonstration. As Etienne mentioned, my name is Mehrdad Kazantarizi. I'm a simulation specialist at OPAL-RT with emphasis on smart grids and communication protocol. You're going to be seeing a demonstration of an example that we have made, which is hardware in the loop testing with a wide area controller with the HyperSim model running on the cloud infrastructure that Etienne mentioned. So I hope you enjoy it. Hello everyone, my name is Mehrdad Kazantarizi. I'm here to show you a demo, the cloud-based EMT simulation for wide area control hardware in the loop testing. The demo is to highlight the HyperSim's capability by leveraging its cloud infrastructure to run electromagnetic transient simulations on large-scale power systems in hardware in the loop setting. The hardware configuration looks like this. The HyperSim model that we use is HyperSim on demand. It's the cloud product of OPAL-RT, and is running on Windows on a server. We have a connection to the server through another device that acts as our controller. This device is an SEL 3360 industrial computer. It has a Linux operating system and has RT Lab installed on it. The RT Lab model acts as the controller and enacts the wide area control algorithm that we have devised for it. It can communicate with the HyperSim model on Windows through the IEEE C37.118 communication protocol. Those are basically the phasers of the different measurements that is receiving, and also through the Modbus TCP communication protocol that acts as the control signals coming from the controller back to the network to enact the control algorithm that I mentioned. In the same area as the controller and the cloud server, we also have a computer setup, a PC, that it has the GUI for RTLab, so it can be used to run the controller model on it through RTLab. And it also has the LabVIEW panel that acts as the HMI for us. The LabVIEW receives the measurement from the HyperSim model, and it can also be used to initiate different protection scenarios that we have made for this wide area control system. Now, my laptop, I can have a connection to the cloud server through the virtual machines. So I can open a virtual machine and open HyperSim and run the model on Windows. I can also have a remote connection to that PC that has a LabVIEW on it, and then open LabVIEW and run the basically initiate the scenarios and receive the measurements from HyperSim. I don't need to run RTLab on that PC necessarily. I can run RTLab from my laptop, because the RTLab model will run the simulation on the SCL controller. So that is the hardware configuration. The network itself is an IEEE 118 bus network. It is a standard network and is used by researchers to for different types of research to enact or implement their ideas for control for different types of studies. That is the one that we have used as well. This network, you can see a concise version of it, of the diagram here. It contains 4 distributed energy resources, or DERs, such as the 2 Type 3 wind turbines. You can see the one here at this bus and the other one at the one of the buses at this location. And also it contains 2 photovoltaic voltage arrays, or PV panels, as we say. One panel here and the other one here. You can also see a lot of or numerous synchronous machines connected in the network as well. There are capacitor banks in the network as well that participate in the wide area control scenarios that we have made. The capacitor banks are there to compensate for an undervoltage that might happen due to a fault at the POC, or point of connection, of the DERs at different buses. The faults that you see here, they are also part of the wide area control scenarios that we can run, and they can cause the undervoltage that I mentioned. And the breakers for the capacitor banks are normally open, so they should the capacitor banks are not connected to the network yet. And once they're only connected if the voltage drops below a certain threshold and causes an undervoltage for a long time, and then they connect and rectify the situation. Okay, so let's check out the HyperSim model. Right now I'm connected to the virtual machine, as you can see by this indication here, and I have opened the model here. This is the IEEE 118 bus network that I mentioned. It is imported from PSSC to HyperSim. It's mainly full of lines and transformers and machines, but it has numerous synchronous machines and the 4 distributed energy resources that I mentioned, or DERs. At each DER, there's a PMU located. The PMU is the phasor measurement unit, and it gathers raw values from the bus or line that is connected to and transforms them into phasors and sends the magnitude and angle of the phasors to the controller. If we find one of them, I try to zoom in. Here we go. So this is one PMU that is located close to the wind turbine 1, type 3 wind turbine. You see it's connected to the voltage bus of bus 32, and it's basically sending the phasors back to the controller. Now we can check the capacitor banks. The capacitor banks that we have in the model, there are 4 of them in the model, but there are 2 that we work with in our algorithm. The the capacitor banks are there to compensate for any type of undervoltage event that might happen because of a fault. As you can see, the breaker that connects the capacitor bank to the rest of the network is normally open, so the capacitor bank is not part of the network yet. The signal to control the breaker to close it and switch on the capacitor bank to the rest of the network is coming from the controller. The communication protocol for this signal is Modbus TCP, and it's coming directly from the model that is running on the controller side. So if a fault occurs and our control algorithm, our wide area control algorithm, works as intended, there's an undervoltage and the capacitor bank will be switched on by closure of the breaker, and so it will compensate the undervoltage and rectify it. Now we look at the RT-Lab model. This is an overview of the RT-Lab model, as you can see, of the controller. The communication protocols, one of them is a C37118. That's the master side on RT-Lab side because it's receiving the measurements from the PMUs. So you can see the PMUs here. The other one is Modbus master. That's for the RT-Lab to send the signal back to the network. The signal that it sends are the signals to close the breakers for switching on the capacitor bank in the network in case of a voltage. The model itself contains the wide area control algorithm that we have devised, that it detects the undervoltage. If voltage drops below a certain threshold for a certain period of time, the logic will work as we have devised it and will send the signal back to close the breaker. Now we can take a look at the HMI for the LabVIEW panel that we have made. The LabVIEW panel, as I mentioned, it's located on the PC that is in the same area with the cloud servers and the controller, the SCL3360 controller. As you can see from here, I'm remotely connected to that PC, and that's where I can open the LabVIEW panel. There are 3 pages on this panel. One page is the single line diagram. The breakers and the faults that you can see here, the default color is green, but they will change color. If they're red, it means that they're closed. We have also a scenario selector that is controlled by a knob. So steady state, as it self-explanatory, is steady state. And the different scenarios, I will explain them shortly. The plant measurements, these are where we can view the RMS voltage and current and active and reactive power coming from the 4 plants that we have devised, the 4 DR plants. So the wind turbines and the PV arrays. And the SM measurements, here we can view the speed and excitation voltage of the synchronous machines that are connected at in the network. The machines that we have chosen here, every row, they show 2 machines of the same area. The reason for this is to see how the machines react to different scenarios, and if they're in the same area, their reactions should be similar. So now let's run the demo. I have to go back to HyperSim and start the simulation. As you can see, the simulation, the target is localhost and it's in real time. So that means we're running it on Windows. Okay. Then I have to start the model for the controller. So I'm back here. I'll just load the model. And I will execute. Okay, so that's the controller model. Now I can go back to the HMI panel in LabVIEW, type the IP address of the virtual machine, HyperSim, and run it. There we go. So now you can see the color of the breakers at the line and the breaker at the synchronous machine have changed to red, which means that they're closed. So the line is operational and the synchronous machine here. But the breakers at the capacitor banks are still green, which means that the capacitor banks are not inserted in the network yet, and they are not connected yet. The plant measurement and the synchronous machine measurement, we can see the measurements coming in. It starts from 0 as a default on the lab view panel, but as you can see, we're getting the correct measurements for the plants and for the synchronous machines. We can do the scenario, the protection scenarios now. So scenario 1. Scenario 1 is to apply a 3-phase fault at bus 23. You can see this fault number 1 here. And this causes an undervoltage that is observed at bus 32 by the PMU. It is located at the point of connection of wind turbine 1. So the PMU is sending the C37 measurements, the voltage and current measurements to the controller. The controller logic, the algorithm, will work as intended and will send the signal to close the breaker for capacitor bank 1. So thus inserting the capacitor bank to the network and compensating the undervoltage that has occurred. So if we change the scenario selector to scenario 1 and do an execution, we should see the color changing from green to red. There we go. And if we look at the plant measurement, so we see wind turbine 1, that's the one that I mentioned would see the undervoltage. You see the voltage drop to about 0.6 per unit, but it didn't stay at that level. Because the capacitor bank was switched on, the voltage was risen to about 0.7, I think, or 0.8 per unit. And then when the fault was cleared, the breaker opened, and that's where you can see this little spike here as well. On the PV2, you can see some undervoltage, but not a lot to justify the closing of another breaker and inserting another capacitor bank. We can see the same situation at the wind turbine 2. And on PV panel 1, you see that it didn't notice the undervoltage at all because it's quite far away from where the fault occurred. So that's scenario 1. And on the synchronous measurement side, you can see the speed is pretty much at 1 per unit consistent, but you can see a lot of transients or spikes in the excitation voltages, and we will view them closely in different scenarios, in the other scenarios. Okay, scenario 2. In this scenario, another 3-phase to ground fault is inserted at the line between bus 38 and bus 30. But after the fault is applied, after a very short time, about 0.5, 0.6 seconds, the breakers at either side of the line will open and disconnect the line from the network. So by doing this, they will basically remove the fault from the network. And while the fault causes an undervoltage, but it's not for a long time to justify the closure of the capacitor banks, bank 2 and bank 1. So let's execute the fault and see what happens. There we go. So you see it was very close, very close that the fault happened and the breakers have opened. If you check the plant measurements, we can see the undervoltage of at bus 40 and bus 32. But since the breakers have already opened and disconnected the line and the fault from the network, there was no need for the capacitor banks to be switched on anymore. So we only see a drop at a very short time. The synchronous measurements, we can see the effects on the excitation voltage of the synchronous measurements. And as you can see, the measurements for 2 machines in the same area are very similar. Scenario 3, the last one. The last scenario is to disconnect one of the synchronous machines from the network. The one that we disconnect is this one, synchronous machine 25 from bus 25. We will open the breaker and for about 5-6 seconds or more, and then we will see the effects on the plants and the other machines. On the plants, there won't be enough. Disconnection of loss of power of one synchronous machine is not enough to again justify the closure of the circuit breakers for the capacitor banks or their insertion into the network. But we will see the effects on the other synchronous machines. So I will just change it to scenario 3. I will do an execution and go to SM measurement tab. There we go. We see the breaker is open. If I go here, now I can see the effects on synchronous machine 26, which is closer to 25. And the spike that you just witnessed was when the breaker closed and the synchronous machine was back in the network. We can see the effects on the other machines, and as I said before, since every 2 machines in the row are from the same area, we see very similar patterns in the excitation voltages. So by doing these 3 scenarios, we witnessed the wide area control algorithm performing as intended by bringing capacitor banks into the network during an undervoltage event because of a fault. And we also managed to see the effects of removal of machines or lines on the other synchronous machines in the network. And all of this was done through the communication between the controller model in RT-Lab and another device and the HyperSim model running on the cloud. Okay, everyone, that was the end of the demo. Thanks for your attention. I hope you learned and enjoyed it. For more information, please go to our website, OPAL-RT.com. See you in the next one.
All right. Thanks a lot, Merdad, for this very good work. I'd just like to remind everybody, if you already have any questions, feel free to use the Q&A section at the bottom of your screen to send them in. I'll say a few more words before we move on to the Q&A session. So where to apply this capability that we've just demonstrated today? There are a couple of ideas. There are certainly more, but this is just to jot your mind and make sure that you think about it. So in terms of advanced education and training, this capability could be used, for example, for simulator rental for the duration of classes as required to finish project, thesis, or degrees. It can be applied to courses and laboratories where each student would have their own simulator for the time required without having to pay for a full HyperSim or RT-Lab license. It can also be used for training large groups of operators, utility resources, and technicians for emergency situations related to protection and control. There are other examples where cloud-based simulation, whether SIL, HIL, or CP can be used. So there's also accelerate prototyping, development, and testing of power system and equipment in a hybrid cloud on-premise setup, like what we just showed, or a cloud-based control algorithm. Also, when everything is fully cloud, we know there are more and more people working on algorithm directly using cloud technologies. So it makes the setup easier by having a cloud-based simulator. Can also integrate with cloud-based AI, machine learning, data lakes, or other post-processing tools. It helps to accelerate testing through secure parallel execution of simulation tests on multiple cloud simulators. So in the end, the bottom line is OPAL-RT can provide your platform for complete testing from imagination to real time. Just a reminder, if you hadn't seen that before, we had presented that some time back. It's an example of performance where HyperSim was benchmarked against another offline tool using the Brazilian transmission grid as a benchmark, where typically in real time on a dedicated hardware would run on 9 cores at 50 microseconds with IOs. We are speaking of a 950 3-phase buses model with 16 12-pulse converters and 500 transmission lines. So comparing the performance going on the cloud With HyperSim on demand, we could achieve 20 times faster than real time on 16 cores, whereas with another tool, another offline tool was 500 times slower than real time. So HyperSim is really 1,000 times faster than other tools that are available to simulate on the cloud. So some highlights to conclude. You can run power system models in accelerated or soft real-time mode, as we've shown today. You can access your simulation environment 24/7, 365 days a year, facilitating working remotely using simply a web browser. You can avoid hardware maintenance and share resources between employees. You can achieve staggering performance gains over desktop-based software and even benefit from a cyber-secure environment. So if you're really interested to know more and set up something like this in your lab, feel free to contact us either through your local contact or through our contact us form on our website. We'll be happy to help you with your projects. So that will be all for the presentation. We'll answer some questions.